Okay, it is 2:01. Again, thank you everyone for joining us. Just a quick overview. Today's webinar, if you're an attendee, everyone is pre-muted. The chat box is only used for broadcast messages. If you have any questions, please direct them to the Q&A box. Again, there's a poll open. We're going to close that in about another minute if you could submit an answer. The webinar is being recorded and it will be available later on the EPA Emergency Response Research Webinar Series webpage, which we will put the link in the chat box for anyone who hasn't seen it yet. If you have any technical questions, problems with Zoom, you can also put those in the Q&A box. And either myself or Denise on the panel will be able to help you with that. If you're interested in receiving the slides, please email EPA Webinar Series at ICF. We'll put that email in the chat box. Certificate of attendance will come from the EPA within 2 weeks. And with that, I'm going to kick it over to Char Bowling, who's going to get us going.
Okay, thank you. So good afternoon, everyone, and welcome to today's webinar, COVID-19 Electrostatic Sprayers and Foggers for Disinfectant Application. The last 15 minutes of this webinar will be reserved for questions and answers on this presentation. Anyone on today's webinar may receive a certificate of attendance. You will need to attend this live webinar for 60 minutes. If you did not request a certificate of attendance upon registration and you would like one, please send an email to EPA Webinar Series at icf.com. That email is on your screen. And just a note that EPA cannot guarantee the acceptance of certificates by your organization, nor can certificates be provided for viewing the webinar recording. EPA is virtually hosting its International Decontamination Research and Development Conference, November 1st through the 5th. The conference website is available. It's on the slide there. Thank you for being with us today. And now it's my pleasure to introduce our speakers for the webinar. Mr. Joseph Wood, Senior Research Engineer, focuses primarily on the development, testing, and evaluation of technologies for the decontamination of material contaminated with biological agents and biotoxins. Joe also investigates the persistence of biological agents, as well as treatment and disposal of waste materials contaminated with bioagents. Dr. Matthew Magnuson, a research chemist, is currently involved in Homeland Security programs related to analysis and environmental fate of chemical, biological, and radiological contaminants. A major focus of his work is management and treatment of large volumes of CBR contaminated water and wastewater. And now I will turn it over to our first presenter, Mr. Joseph Wood. Thank you.
Thank you, Shar, and good afternoon, everybody on the East Coast, and good morning for those on the West Coast, western part of the U.S. It's my honor to talk to you today about a project that we've been working on over the past year related to application of disinfectants using electrostatic sprayers and foggers. I appreciate everybody's time being here, and hopefully we can provide some good information for you. Next slide, please. So this work is the result of a big team effort with, wanted to give a shout out to folks in our laboratory support folks from JTI, Jacobs Technology, and then you see their names there. And then EPA folks from EPA's Office of Research and Development, Office of Emergency Management, Office of Pesticide Programs, and EPA folks from the regional offices. It's been a big team effort, and the EPA folks have provided a lot of input on where the project should be going and that sort of thing. Next slide. So for the outline of the presentation, what I'll be talking about today, myself and Matthew, I'll give a little bit of a background on why we're doing this work, and then we'll jump into some of the evaluations that we did, looking at things like droplet size distribution and loss of disinfectant active ingredient, that sort of thing. We'll spend a little bit more time on the deposition and related tests, and then we'll talk about some disinfection efficacy tests, and then we'll wrap up the presentation. Next slide, please. So a little bit of background on why we're doing this project. I think everybody's read in the news lately that by and large, the thinking is that COVID-19 is primarily transmitted through the SARS-CoV-2 virus by airborne mechanisms, but there still is a small chance that contamination can be picked up by contact with surfaces. And so the U.S. Centers for Disease Control and Prevention recommends that surfaces be cleaned and disinfected. So when the COVID outbreak started, there was a lot of use, and you saw it in the media, on TV and that sort of thing, about electrostatic sprayers and foggers being used. And the advantage of those is that they're generally powered sprayers, and so large areas can be disinfected rather rapidly. And then also, because they apply an electrostatics charge, there's thought that that charge could allow for the spray to contact surfaces not directly in front of the sprayer. So looking at the wraparound effect, that sort of thing. Next slide, please. So in a nutshell, what we are trying to do with this project is, excuse me, evaluate some of the underlying operational parameters that these sprayers and foggers related to the use of disinfectants, application of disinfectants to surfaces. Next slide, please. So there were a number of parameters that we looked at. Not all of the devices were evaluated in this project, but we looked at electrostatic spray charge. We looked at loss of active ingredient of the disinfectant when you spray it. And then we looked at things like deposition and how much of the disinfectant should be applied to the surface. Next slide, please. So another reason or background for this project was there was health and exposure concerns with the folks that are using these sprayers, or the folks that entering the spaces after the disinfectant has been applied. Things like exposure to the active ingredient of the disinfectant. It may be inhaled as a vapor or gas, or through the droplets from the sprayer. And so for that reason, droplet size distribution of the sprayers was measured. The smaller the droplets are, the more readily inhaled they can be. And consequently, EPA's Office of Pesticide Programs, their guidance indicates the sprays from electrostatic sprayers should have a volume median diameter greater than or equal to 40 microns. And we'll talk a little bit more about the VMD in a bit. Next slide, please. So this is a rundown of the devices that were tested. As you can see, we tested a number of electrostatic sprayers. We evaluated 2 foggers and then 1 garden sprayer that was not electrically charged. And that was just sort of a baseline look at that type of sprayer. But most of the sprayers electrostatic sprayers that we looked at were powered by battery. There were a few that you plug in and were AC powered. The hand pump sprayer was not electrically powered. And then a couple of the notes of the devices that we looked at. One of the devices had the ability to turn on and off the electrostatic charging. So in some of the evaluations, we looked at the impact of whether it was on or off. And then another one of the electrostatic sprayers had, you could adjust the nozzle size to impact the droplet size distribution. So there was 2 nozzle sizes that were available for that sprayer. And so we looked at droplet size distribution, excuse me, with both nozzle sizes. And then a couple of other notes, a few of the sprayers had issues with their lithium-ion batteries. So next slide. And then I am going to turn it over to Dr. Matthew Magnuson, and he's going to run through some of the slides talking about some of these parameters. So take it away, Matthew.
All right. Thanks, Joe, and thanks to everyone who's tuned in this afternoon or this morning. The next few slides are about the droplet size distribution test, which we performed in-house on the sprayers that Joe just talked about, using similar to a method by the ASTM International, which is a standard-setting organization that publishes methods for doing these sorts of things. So we measured the droplet size distribution with tap water and deionized water and a few disinfectants, because on the next slide, we wanted to get a look at this thing called the volumetric mean diameter, which is more or less a measure of the cumulative size distribution that you see here on the left. And so when you spray these things, you don't just get one size of droplet, you get a lot of size of the droplet. And so there's a distribution that you see on the chart, and which is then through some formula expressed as the volume mean diameter, or VMD, which is what you see on the right side of this corner. So it's some measure of the particle size, and then is important in those health-based calculations, because you don't want to inhale particles of a certain size based on how the respiratory system works. But at any rate, essentially what you see here is that, most of these devices did, for the most part, give particles greater than 40 microns, which is the cutoff limit established by the experts. And there are a few that maybe gave a little bit smaller. So that's interesting. And then on the next slide is some additional summary points. And then, so when you're spraying these things, you don't have your sprayer on a tripod like you see in the picture. You're moving this around so that there's a distance that you're spraying, and it turned out, fortunately, that the VMD, the volume mean diameter, did not decrease so much with spray distance, so that's good. It also turned out that the water source or disinfectant didn't really impact the droplet size distribution, which was a little surprising, because one of the aspects of charging the particles is in principle, can lead to smaller particle sizes, but that's not what we observed. Nor did we observe that when you change the nozzle for those devices that you could change the nozzle, that the size changed very much. So all in all, we noted that sprayers do typically report a droplet size, but it's not really clear how they're all determined. So it may be difficult without tests like ours to do an apples to apples comparison on the particle sizes that these devices are producing. So on the next slide is another set of results related to loss of an active ingredient. So the idea here is that when you spray make the spray, particularly with a disinfectant, that you increase the surface area and therefore the potential evaporation rate. And so potentially you could get gaseous disinfectant and be breathing that in. So we looked at a particular one of the handheld spray devices, and looked at some active ingredients, and also looked at several different positions away away from the immediate spray location, so at the reservoir and at the nozzle, and again 3 feet away. So this gives an indication of people's potential exposure to these disinfectants if there is a loss during the spray process. And on the next slide are some of the results. Essentially, this is for hydrogen peroxide. So for the most part, you know, when you spray them, they do stay below the permissible exposure limit, which is some health-based limit that's a standard value or standard concept regarding exposure to vapors in particular. So that's some good news. And then on the next slide is for another disinfectant, a chlorine-based disinfectant. It's dichlor, so it's that disinfectant that it's like that's used in swimming pools. That's a form of stabilized chlorine, but does release free chlorine during use. And then you see here the disinfectant concentration in parts per million at the various locations, and then the maximum vapor that these are the free chlorine as measured in the liquid phase, but the vapor concentrations were again below the permissible exposure limit to the best we could measure those with some electrochemical sensors in the air. So in the next slide, we look at a very important part of electrostatic spraying, and that's the droplet charge. So the idea behind the electrostatic sprayers is they impart a charge onto the droplet, which, as Joe mentioned, has in principle some advantageous effects for the application of sprays, and also has been for certain applications demonstrated to really have significant advantages for electrostatic spraying. So it's important to investigate these in some detail. So the physics of electrostatic spraying and the resulting effect is really a complicated matter. So this exploration was mainly about you know, how much charge is actually imparted on these droplets. There are many other sorts of analysis that you could do, but we hope that the ones we did here did provide a good flavor of at least the ability of these devices to produce sprays. So on the next slide, we show some of the spray charge results. There are several take-home messages here. First of all, if you look at the first two rows, this one device had a switch that you can turn this electrostatic spray on and off, and the measured charge with it on is higher than the measured charge when it's off. And you might argue that the measured charge when it's off is simply within the error in the measurement. So that's good that it is charging. You know, we measured this charge with a pretty standard technique you see in the literature, but it isn't really. There isn't like an ASTM standard technique for that. So this is what you know you see people use, but there's some variability. Therefore, that when people report charges, but nevertheless, since we use the same technique on all of these, at the very least, these are consistent. So these devices generally produced charge, and when it's a positive number, it's a positive charge, and when it's a negative number, it's a negative charge. And then I'll also point out before going to the summary slides on the next. The summary results on the next slide, that I'll point out this total 360, and you see that the charge is you know several times greater with and without a disinfectant as opposed to just DI water and tap water, and that's perfectly consistent with the underlying physics of the charging phenomena, but also illustrates that. Yeah, when you actually use a disinfectant, it doesn't pick up the effects of the charging may not be as great, and again that's perfectly expected. So on the next slide are the high-level results. But the first is kind of a caveat, is that, despite the numbers we measure, regardless of how people measure them, it's really not clear how much of a charge to mass is necessary to cause the benefits of electrostatic deposition of disinfectants. In other applications, such as application of pesticides to plants, really a kind of small charge is needed. But then that's a different application, and when you're applying a pesticide, you don't really need to completely cover the plant leaf, since it's taken up into the plant's system. But nevertheless, if we go with that number as a benchmark, at least 4 out of the 6 ESSs, even measured with our technique, did achieve that value, and a number of those were fairly close. We'll note, and it's just kind of a note, is that the plug-in devices tended to have a higher charge, and so you might expect they would have, at the very least, an enhanced effect. And in many respects, that's also consistent with the physics of these droplet formations, because in the plug-in ones, the plug-in also runs an air pump, which injects some air through the spray tip and pneumatically assists the charge, so that assists the formation of the spray. So maybe it makes finer spray and picks up higher charge per spray. I will say the technique that we have illustrated in the slide is just for the overall charge and can't differentiate the particle size effects on the charge, which is a very complicated experiment, and which isn't very often reported, but does lead to some very interesting physics results. So maybe the final bullet here to point out is, and I tried to point this out on the previous slide too, is that you really do get a drop in the charge, charging the droplets when you go to spraying disinfectants, which again is consistent with the underlying physics, but also highlights that to properly understand how well your sprayer is working, you may need to make sure that the results are being represented via the use of disinfectants as opposed to even tap water. So on the next slide, we get back to, I'll turn this back over to Joe, because it deals with that whole issue of maintaining wetness, which is what you want to do for any sort of spraying disinfectant. So back to you, Joe.
Okay, thank you, Matthew. Yes, so we're gonna move to talking about deposition and how much of the disinfectant should be applied to an area. And the main points to bring up are that the surface needs to remain wet for the required contact time of the disinfectant, and if the surface is visually dry before the end of the contact time, then the disinfectant needs to be reapplied to maintain wetness for that contact time. So there's a bunch of different information out there about how much of the disinfectant should be applied to a particular surface. Some of the vendors provided information on how much should be applied per 1,000 square feet. Another vendor recommended that you do a wetness test to see if the surface remains wet for the contact time, and that's what we did, and I'll talk about that next. And another vendor recommended spraying the surface until the droplets start to coalesce. So we also kind of followed that advice as well in some of our tests. Next slide, please. So one of the tests that we did was just a simple test to spray a surface and see if it could remain wet for 10 minutes. And 10 minutes is kind of a typical contact time for a lot of these disinfectants. So we use 5 different sprayers using water, and we use, excuse me, 14 by 14 inch square coupons oriented either vertically or horizontally. And we spray the coupons with water until the droplets started to coalesce. We use different types of materials for the coupons. And then, so immediately after spraying, for some of the coupons, we wipe them right away and then weigh the wipes to determine how much mass was there initially on the coupons. And then other coupons, we did that same technique after 10 minutes to see how much water was lost. And then, so for the, evaporation of the water or the disinfectant is highly dependent on environmental conditions. So you see the environmental conditions listed there. Next slide, please. So here is a summary of some of the results that we got from these wetness tests. And in the figure you see, the y-axis, the bars are showing how much mass or milliliters of water was recovered from the coupon for the different materials, stainless steel, glass, and plastic. And then the orange and green are the horizontal coupons, and purple and yellow are the coupons oriented vertically before and after the 10 minutes. So some of the things that we found were that coupons in the horizontal position generally had a higher initial deposition. And that kind of makes sense since you could get runoff with vertically oriented coupons. So when we sprayed the coupons, the positive controls, we followed the advice of spraying until things started to coalesce. And when we did that, the amount of water that was initially deposited on these coupons was in the range that that was recommended by the vendors. So in terms of percent water loss, we did see higher loss, a little bit higher loss, percent loss from the vertical coupons. And then we did see some effect of material on the evaporation rate, and plastic had the least amount of water loss. Next slide, please. So some other results that we found, overall 13% of the coupons were completely dry after 10 minutes based on the gravimetric method that we used. We did see that a good number of coupons, they did not dry evenly. And so there was parts of the coupon that looked dry, but if, based on our gravimetric method, our white method, it did report that there was still water on the coupon. And then you see there, something I alluded to earlier, there are many factors that can affect the drying time, and you see those there. The initial amount that you apply to the surface, and then the environmental conditions, the material, and then how readily the disinfectant can evaporate, and then the droplet size. The smaller the droplets, the faster that the liquid can evaporate. Next slide, please. So we looked at a black light test method to qualitatively assess the wraparound effect, how much of the spray was depositing on a cylindrical object. And we used a 8-inch diameter black trash can, and we sprayed an aqueous solution of fluorescent dye. And then after spraying the trash can, we illuminated it, turned off all the lights, and then illuminated it with a black light. And then we, excuse me, we photo documented the can, all 4 quadrants of the can. And then for the whole can, and then 3-inch by 3-inch squares on the can. And then after those tests, we looked at more everyday objects to see what sort of deposition we would get with those types of objects. Next slide, please. So these are some example results that we got. On the left side are the positive controls. These are the cans that were not sprayed. And you could see those are 3-inch by 3-inch squares, and you can see the front, the right, the left side, and then the back of the can. And then on the right side of the slide, you see the can that's been sprayed, and you could see the front of the can obviously shows a lot more illumination, and you could see the droplets. And then you can see a little bit of the right side and left side, a little bit of deposition going on there. But then the back side of the can, very, very little deposition at all. Next slide. So we moved on to other objects, and just as example results showing here, the lamps, a laboratory clip-on lamp. And so you could see, the deposition on pre-spray. The lamp looks pretty dark, but on the right side of the figure, you can see the deposition from the lamp, and even underneath the lamp, you could see some illumination indicating that there is a little bit of deposition. But overall, the deposition was pretty similar for all the different types of sprayers that we evaluated. And we didn't really see the wraparound effect that we were hoping to see. It wasn't as pronounced as we were expecting it to be based on the discussions of these electrostatic sprayers. And then the smaller objects did show a little bit of a more of an effect of the wraparound effect. So next slide. So, excuse me, we did look at trying to quantify a little bit of the deposition. So we used leaf wetness sensors, and we just did a few tests with these. We just used one sprayer, and the readout from these sensors, it gives you a percent surface coverage, percent wet of the entire surface, and we correlated that to mass, and that correlation was pretty good. So in these sensor tests, we placed the sensor directly in front of the electrostatic sprayer, and then we also sprayed it when the sensor was turned 90 degrees, and then when the sensor was turned all the way around 180 degrees to see what sort of deposition we would get. Next slide, please. So these are just some example results from one of the tests that we did. So on the y-axis on the bars is showing the mass that was recovered from the sensor. And then on the x-axis are the spray times of 1, 2, 3, 4, and 5 seconds. And then the blue bars are when the sensor was directly facing the sprayer, and then orange is when it was on its side. Excuse me. And then the gray bars represent the recovery of water when the sensor was turned all the way around. So there is a little bit of deposition going on when the sensors turn 90 degrees, but when the sensor was turned completely around, very little deposition was seen on that. So quantifying a little bit better quantification of the wraparound effect, that we didn't really see much wraparound effect, a little bit, but not a whole lot. And this was just one test from one sprayer. Next slide, please. So the last set of tests that we did was just a few disinfection efficacy tests. And what we did was, what we wanted to do was compare a trigger pulse sprayer, a non, off-the-shelf sprayer, a non-electrostatic sprayer with a handheld electrostatic sprayer. And then with the electrostatic sprayer, we used the one where you can turn on and off the charging. So basically, we were essentially evaluating 3 devices in these tests. And then before we did the efficacy tests, we did some spray tests beforehand, just to ensure that when the coupons that we use for these efficacy tests, when they're directly facing the sprayers, we wanted to make sure that the 2 devices deposition was similar. So we found that 2 trigger pulls at 1 foot away provided the similar amount of deposition when we did a 2-second spray from the electrostatic sprayer, and that gave about 0.03 to 0.04 grams per coupon. Next slide, please. So what you see in the picture there is the coupon, the size of the coupon that we used, and we used steel coupons and glass coupons of that size. They were 1 inch by 1 inch. And then for the disinfection efficacy testing, we used the CDC dilute bleach recipe, and that provided about a 2,000 ppm free available chlorine concentration. We used, as the microorganism, we used the 5,6 bacteriophage as a potential surrogate for SARS-CoV-2. The main point of these tests was not really the true inactivation of the bleach recipe, but more to compare the trigger sprayer and with the electrostatic sprayer when it was on and off. That was the main point of these tests. And then, so for each test coupon, for each test condition, we use 3 replicates. Next slide, please. So these are a summary of the results we got. Excuse me, and a lot of stuff is going on here. But what you see on the left side of your screen is the deposition. That's the amount of water that was applied to the coupons with spraying. And on the right side of the figure is the log reduction. The PFU stands for plaque forming units. That's the way to quantify the virus. And then, so in the charts, the top part of the charts is when the coupons were directly facing the sprayer. And then the bottom part of the charts is when the coupons were turned 90 degrees. So, and then we were showing the results for the 2 different materials, glass and stainless steel. And then for the 3 devices, in the orange, we have the trigger sprayer, and then green is with the electrostatic sprayer on, and then purple is when it was off. So one of the main points we got from this excuse me, experiment was that the efficacy was strongly correlated. The log reduction in activation efficacy was strongly correlated to the deposition. And oh, by the way, the top right chart where you see ND, that's non-detect, and that's where we were unable to recover any of the 5,6 phage. Another point to make is that when the coupons, the top portion of the charts, when the coupons were facing each other, there was very similar results in efficacy when the coupons were directly facing the sprayer. And then when we turn them 90 degrees is when we start to see some interesting differences in results. And you could see that the electrostatic sprayer, whether it was on or off, did better than the trigger sprayer. And then we'll go to the next slide, Shar. And these are kind of some of the things I was just saying, but so whether when the coupons were turned 90 degrees, we did see similar results regardless of whether the electrostatic sprayer was on or off. And this may have something to do with you know, the droplet size and not necessarily the electrostatic charge imparted to the spray. So let's see, next slide, please. So overall, in summary, some of the key points from the study, just to, you know, to summarize again, the purpose of the study was to evaluate several different devices, electrostatic sprayers and foggers, and some of the underlying physical parameters, some of the chemistry related to the use, related to their use for application of disinfectants. So there's many things that can affect the deposition of the spray and how it gets deposited, how much of it gets deposited on a surface. And we touched on those, and a number of things can affect that and whether it can remain wet for the required contact time. From the efficacy tests, like I just talked about, the decontamination or disinfection efficacy was highly correlated to the amount of disinfectant deposited on the surface. And then getting back to the droplet size distribution stuff, most of the devices that we did evaluate did have the volume median diameter greater than the 40 microns. Again, the 40 microns was a EPA Office of Pesticide Programs criterion. Next slide, please. And then for the some more takeaways from the study, 4 out of the 6 devices that we tested for charge did produce charge of their sprays above the 0.1 millicoulombs per kilogram, and that's kind of an amount that we got from the literature that indicated the minimum amount where you could expect maybe some electrostatic benefits. 2 out of the 6 that we evaluated, interestingly, had a negative charge, while the other 4, the 4 that were battery operated, carried a positive charge. And we didn't see a whole lot of the wraparound effect when we sprayed the 8-inch diameter object, even for the electrostatic sprayers that had the highest excuse me, had the highest charge, and not listed there. But when we did the wetness test with the wetness sensor, we kind of saw the same results. There wasn't a whole lot of deposition when the sensor was turned completely around. There was a little bit of deposition when the sensor was turned 90 degrees. And then for the few tests that we did related to loss of active ingredient to the air, for the hydrogen peroxide disinfectant, dichlor disinfectant, we didn't see that as a problem. We didn't see a whole lot of loss to the air, and consequently, there wasn't much loss of the actual disinfectant active ingredient concentration either. Next slide. So as scientists, when we do a research project, we uncover other things that we want to look at. So I think there's room for more research to delve into the electrostatic charge of the spray and dig deeper on that, and whether some of these parameters are affected by or the electrostatic charge, things like or are affected by the electrostatic charge, things like deposition and disinfection efficacy, that sort of thing. So there's more work to do. Let's see, next slide, please. And that is it. So thanks for everybody's attention. And you could see, excuse me, you could see the URL there to EPA's Code 2 research website. If you scan that QR code with your phone, that'll take you to that same URL. And that is it. And thank you, everybody. And I guess we'll entertain some questions.
Sure. Hey, Joe. This is Lonnie. We have a bunch of questions, but I know there were some about what is the difference between an electrostatic sprayer and a fogger or mister. And I just want to state that EPA and CDC have agreed that an electrostatic sprayer is a device that works by applying a small electrical charge to aerosols when passing through the nozzle. And these charged droplets adhere easier and stick to environmental surfaces. And we've also defined a fogger, also known as a mister, as a device that uses a fan and a liquid solution to create a fog or aerosol with small droplets or mist. Hopefully that answers all of those questions.
Right. And the foggers that we tested were not electrostatically charged. And another thing about the foggers is, at least for the work that we've done with foggers, is that they're more of a technique to disinfect volumes or aerosols, large spaces of the air, and not necessarily, they could do surfaces, but it's also fogging can be done for open air areas.
Thank you. So Joe, do you know why OPP chose 40 microns VMD, which I forget what that is already, as the cutoff?
Yeah, we're Lonnie. Yeah, I don't know if we want to get into the policy of that. I don't know where that cutoff came from, but
Okay.
the main point is that the smaller the droplets, the more readily inhaled they are. So it's a exposure concern issue.
I think that's probably the right answer.
I would refer them to OPP.
Well, yeah, definitely. Were the tests conducted with a trigger sprayer as a control to see how much is lost there as well?
If they're talking about loss of active ingredients, we did not do that for those tests. We only use the trigger sprayer to compare the disinfection efficacy.
Would you anticipate, I think that's fine. Would you anticipate different results if the experiments were conducted under UV?
Well, the black light uses, that's UVA. So in those wraparound tests with the black light, we sprayed a fluorescent solution that's illuminated by the ultraviolet light in the A range. So we did use the UV. I don't know, maybe they're talking about UVC, inactivation of UVC, but no, we didn't look at UVC as an inactivation technique. That's a different,
right, and that's different research, which we did do.
Yep. And that'll be talked about next webinar, I believe.
Yep. Do electrostatic sprayers have any impact on the adverse operation of electronics?
That's going to depend on the chemistry of the disinfectant, and really shouldn't have anything to do with how the disinfectant is applied, whether it's a fogger or a trigger sprayer or electrostatic sprayer. If the disinfectant is, like bleach, dilute bleach, there may potentially be some material compatibility issues. I don't know, compared to say something like a quaternary ammonium compound. It would depend on the chemistry of the disinfectant.
And that brings up another question, Joe. People were asking about, we're talking about the disinfection process, but we recommend cleaning before disinfecting. And so this research was specifically for disinfection purposes, but if you're trying to clean and disinfect a large area, you'd still have to wipe down everything, right, to clean it and then disinfect after.
Yeah, depending on how you clean it. That's a good point. You might want to use a wipe or a squeegee or we didn't look at the cleaning aspects.
Did you test under various conditions of humidity?
We tried to keep for all the tests that we did in the wind tunnel, and those included the droplet size distribution tests and the charge tests and the wetness tests. We, in EPA's aerosol test facility, we do have control over the relative humidity in that test chamber. So the relative humidity there at those tests was fairly well controlled, and I believe fairly consistent throughout the testing. But in some of the other tests, we did not control or measure relative humidity.
Okay, we've got a lot more questions coming in now. Was there a statistically significant difference between regular spray bottle and electrostatic sprayers?
We didn't do enough tests to make any kind of statistical inference. The efficacy test that we did was just one test with 3 replicates. So you got to take the results that we got with a grain of salt, I guess, from a statistical standpoint. Ideally, if we had more time and funding, we could take a more robust approach to doing those tests. But so statistically, some of the results are up in the air. I don't know, Matthew, do you want to weigh in on that?
Sure. So there's several aspects to that question. So the pesticide program requires different types of testing for ESS application of disinfectants as opposed to regular manual sprayers, like you get the spray bottle off the shelf and the pump bottle. So those are kind of difficult to compare directly in the best circumstances because they are different tests. And as Joe was noting, that really wasn't the intention of this study. The idea, though, behind the different OPP procedures, particularly those that, as Joe went over in some detail involving the wetness tests, is to ensure that the wetness is the same, and therefore the amount of organisms affected is the same. So I hope that adds a little bit additional flavor to the question, because there are many parameters that you might compare when you do those.
Yep.
So we have a question about, was there no difference of electrostatic sprayer disinfectant efficacy with or without the charge?
We did not look at that, and that's actually one of the suggested research, further research that could be done to look at that aspect. There's a whole lot of things going on with the electrostatic charge that may impact deposition and may impact efficacy, that sort of thing. So that's definitely an area of future further research for sure.
Another question was, did you by chance determine efficacy when using only distilled water with ESS?
We did for our positive controls. I believe they were sprayed with water. I don't know if it was distilled. It might have been tap water or deionized water, but I believe to calculate the log reduction, the disinfection efficacy, we looked at the positive controls, how much of the virus was recovered from the positive controls compared to those that were sprayed with the disinfectant. And I think that the positive controls were sprayed with water, and that had no impact.
So is there any advantage to using an electrostatic sprayer as demonstrated in the research?
That's a good question. That's a very good question. I think the jury may be still out. One of the things that we saw was the wraparound effect wasn't as pronounced as we thought it would be based on discussions in the media about it. I think the main thing is if you need to cover large surface areas, you could use a powered sprayer, whether it's electrostatically charged or not. I think that's the main thing. People had talked about using these paint sprayers to apply disinfectants, and any kind of powered sprayer, would give you speed and applying the disinfectant over a large area. But I think more research needs to be done to answer that question fully. But the other takeaway is, since we didn't see a whole lot of the wraparound effect, I think the main point is that the folks that are applying these disinfectants should probably try to do a good job of spraying directly in front of every surface that they want to apply the disinfectant to, and not completely rely on the wraparound effect.
I think that's good advice. The next question, I think, is still for you, really. In the wetness test, is the residual mass representative to remaining amount of active ingredient?
Well, it's a corollary to the actual disinfectant, not necessarily the active ingredient. No, I mean, most of the active ingredients are only a small percentage of the actual disinfectant. Maybe less than 1%. Depends on the disinfectant, but no, it's mainly just the water was just kind of a safe way to, do a wetness test without using an actual disinfectant.
Joe, there's another question about, were all the tests for the battery powered sprayers done with a fully charged battery? Curious if there's a significant loss of electrostatic charge as the battery is losing charge.
Yeah, we when we initially started this test program, we weren't we could have done a better job to ensure that the batteries were fully charged, but after a few tests, we had to go back and make sure that, and after that, all the tests were conducted with the batteries fully charged. So yeah, after I forget exactly how long these batteries last, but I'm not sure. We didn't measure electrostatic charge as a function of battery charge, but the battery charge definitely, it didn't last. It wasn't the battery charge didn't sustain itself over time. It diminished over time, as you would expect.
Right. Joe, another question is, does ventilation in the room affect droplet deposition?
It can, if airflow, if the small, and we actually saw that in our laboratory with the ventilation on, with in certain cases you could see the spray being carried away by the airflow. So and I think the smaller the droplets are, the more readily they're going to be carried away by airflow. So yeah, definitely, yeah.
And Joe, to add to that, that's the same thing that you see in the much larger volume of pesticide deposition literature, which is then very important, when you deal with large volumes in fields and whatnot.
Yeah, they call that drift, spray drift. So that's definitely more of a concern outside with wind, but it's definitely, and that's something that we really didn't look at, but that's something that could be looked at further. But definitely the smaller droplets from the electrostatic sprayers are, would have a higher tendency to be carried away by the airflow.
So I'm going to ask one more question. This will be the last question and we'll wrap it up. And the question is everything on list N okay to spray? And the answer is no, but Joe, I'm going to let you dip into that one.
Yeah, that's more of a question for EPA's Office of Pesticide Programs, but I think there's a specific registration process to use an electrostatic sprayer, but I would refer that questioner to EPA's Office of Pesticide Programs.
And I would even add that when you look at list N, if you follow the label instructions that are on the disinfectant, and on list N, it specifically says whether they could be used for electrostatic sprayers or not. I believe there's 3 or 4 on the list. I'm not 100% positive of the number, but I believe there's a few on there that do state they can be used. But again, list N, not all of them can be. So follow your label instructions for any disinfectant.
Right. Yep. I think you're right. I think there's only, a handful, not too many are registered for application with an ESS for sure. Not too many.
All right, we'll wrap it up there. Thank you everyone for attending our webinar today. And we'll still go through some questions. I saw people were asking for Joe and Matthew's contact information. We'll make sure you have that.
Okay, sure.
And anyway, have a great day. Thank you for attending.
Thank you, everybody. We'll see you.